We present robustness without wrinkles, parallel simulation, and robust MPC for certified deformable manipulation. Manipulating deformable objects remains challenging for real-time model-based control due to their high-dimensional dynamics and non-smooth contact. We propose Chord SLS, a framework for online deformable object manipulation, contact-smoothed differentiable simulator, and system-level synthesis for robust output feedback planning. Each simulation step consists of an unconstrained optimization, followed by a second-order cone program. Both admit implicit differentiation formulations, enabling the simulator to serve as a differentiable layer. However, contact and holonomic constraints introduce non-smooth dynamics due to changes in the active constraint set. To obtain useful gradients, we replace these hard switching events with smooth surrogate functions. Although this introduces some gradient bias, it yields much more informative optimization signals for planning and policy learning. We frame deformable object manipulation as robust output feedback, where the controller handles both model disturbances and noisy perception. GPU system-level synthesis, or GPU SLS, solves state feedback efficiently on the GPU by splitting the robust optimization into two parts, a nominal trajectory and a robust controller. Chord SLS extends this pipeline by adding parallel Kalman recursions, enabling output feedback control directly on the GPU in logarithmic time. To bridge the sim-to-real gap, we use conformal prediction to compute empirical error bounds on prediction error from calibration data collected on hardware. State estimation is performed from RGBD images using a SAM3-based segmentation pipeline and TapNext++ for real-time keypoint tracking. These keypoints are used to reconstruct the deformable object state, enabling our simulator and planner to generate trajectories for hardware execution. We benchmark our approach on 4 deformable manipulation tasks, all of which require the manipulator to establish and maintain contact with the deformable object. The rope dragging task further demonstrates uncertainty-aware planning tubes for obstacle avoidance under uncertainty. Across all tasks, our method consistently achieves lower goal error and fewer safety violations than MPPI, while requiring fewer dynamic evaluations per MPC iteration, resulting in faster planning. Our simulator can also be used for reinforcement learning by providing analytical policy gradients through differentiation of the simulator. Compared to PPO, APG converges in fewer training steps, as the contact-smooth dynamics yield more informative lower variance gradient estimates that improve sample efficiency. Here we show rollouts of a rope manipulation task under simulated measurement and dynamical noise. Despite these disturbances, our output feedback formulation remains robust, with all rollouts staying within the computed tubes. Lastly, we validate our formulation on hardware. On the left, we show a real-time rope manipulation task in which 2 manipulators first acquire a grasp, enabled by our contact-smoothed simulator, and then navigate the rope over an obstacle. In the middle, we show the robust tubes generated by SLS and demonstrate how our method has 0 obstacle collisions despite dynamical and measurement error. On the right, we show our method completing a high-dimensional cloth folding task, demonstrating its scalability to the high-dimensional systems of deformable objects. We conclude with a summary of our work. Thank you for your attention.